Absolutely.
Okay, thank you. So today we want to talk about this confidence interval. It's how people how people should report their results. Where is the chat? So I want to write something here. This is a link for, okay, no, unfortunately not. Okay, so we need to talk about this confidence interval because it's something very important when people report their results, because in fact I was in PhD defense and the PhD student, he got one question from one examiner because he was reporting his results as one number. So I said that I need to really inform you about this to avoid this in the future. When you need to report your results, you should not report your results as a single number, because when it's a single number, it will be very strange. So for example, if I said that my model has accuracy, for example, of maybe, I will not say 95% because we have this 95% here. So imagine that your model has an accuracy, for example, 83%, for example. Just one number. So this is your accuracy, it's 93%. So if I feed my model with maybe 100 images, maybe 93 will be correctly classified and 7 will not be will be misclassified. So this number, it's a very strong claim, in fact, and it's very difficult for people to swallow it. So it's better to try to communicate your results as a range, for example. So it could be, for example, the average accuracy. So you don't need to mention that it's the accuracy, but we need to say that this is the average accuracy. And we will report the mean value plus minus maybe standard deviation, for example. So in this case, we will have a range for my accuracy. So we'll have two numbers, right? So it will go from this range to this range. So it will be more correct, right? But the problem here, if I need to calculate the mean and the standard deviation, maybe I need to run my model n times. It could be standard deviation, for example, or standard error, for example. But in this case, I need to run my model n times, right? Which might be time consuming. But this is how we should do it. But also I will talk about confidence interval and how can we calculate this confidence interval using a single model. So reporting the model accuracy, it's important to report the performance of your model to your stakeholders, because at the end of your modeling task, we need to report our results to our stakeholders or to our readers, for example, if you are writing a publication, for example. So and those numbers, they are the expectations of the model on new data, because we agreed that we will have this validation protocol. We will use hold-out validations or cross-validation, for example. So we will train the model. We have two types of data sets: one set for training and one set for. So we will have the training set. It will be used for training your model, and after that we will have the test set. This test set, we call it unseen data, correct? So it's unseen data. It's a new data because I need to test my model with unseen data or with a new data. So I will test my model using this unseen data, for example, and we will calculate, for example, accuracy. If you report it as a single number, it will be very strong claim that my model, if someone else in somewhere else, he will try to test my model, he will get this number. And it's very difficult to get the same number, right? It's really very, very difficult to get exactly the same number for many reasons. So it's better to report it as a range instead of reporting your accuracy as a single number. So you need to report the classification accuracy, for example, of the model alone. For the test set, for example, imagine it's 80%. It will be a common mistake, because this 80%, it will be very difficult for other people to get the same, to reproduce the same numbers. So, and therefore we need to use confidence interval, and this confidence interval, it provides robust indication of your model skills or performance by providing a range where the true model accuracy may lie outside that. We need to provide it as a range. And in this range, we assume that by 95%, the model accuracy, if someone else will try to reproduce our results, we will assume that by 95%, the model accuracy will lie within this range. But also, it's also true that it could be also possible that the accuracy will lie outside this range. Because if it's so we claim that we are 95% confident that it will lie inside that range, but it means also there is another 5% that this accuracy will not lie within this range. And this is very, very nice way and very professional way for doing it. Because if someone else, for example, you build a model here in Norway, and someone in China, for example, he try to reproduce your results, maybe he will not get the same results, and maybe also the accuracy will lie outside. If it is outside this range also, it will be okay. Also, it will be accepted by the scientific community because you just followed the right approach for reporting your results. So we can say that we will be 95% confident that if you repeat our work, you will get the same accuracy, or the accuracy will be within this range from lower bound to upper bound, right? And also at the same time, we still also have a probability of 5% that this accuracy will lie outside this range. So the confidence interval, it's the mean of your estimate plus and minus the variation in that estimate. So it will be a range. So we will have this lower bound and upper bound. It will be like this one. So we will have two values, and we will claim that it will be located between, it will be within this range. This is the lower bound, and this is the upper bound, right? This is the range of values you expect your estimate to fall between if you will redo your test within a certain level of confidence. And this is the best way for doing it. So now we don't need to report our results as a single value, but we need to report our results as a range. So for example, if you construct a confidence interval with 95%, you are confident that 95 out of 100 times the estimated accuracy or error will fall between the upper and lower values specified by the confidence interval. Right? So, so for example, here, this is, usually people, when I was attending this PhD defense, the PhD candidate, he was reporting his results like this one. And many of us, in fact, we are doing this. So, for example, he has 3 models, and he tried to compare the performance of those 3 models, for example, in data set A, B, and C, for example, and he reported that the accuracy of model 1 is 89%, accuracy of model 2 is 75%, model 3 is 95%, right? So as a single number, because he was testing his model with the test set of data set A, for example, and he will repeat it for data B, he will do it also for data set C. So at the end here in this graph, for example, this is the accuracy. So we have just single value for model 1, single value for model 2, single value for model 3. This is not, this approach, it's not correct. How we should do it? We need to do it as an interval, as you can see in the right-hand side. So we need to have the model, the mean accuracy plus minus maybe standard deviation, for example. So it should be a range, as you can see it here. So which means that if you repeat this experiment one more time, we will be maybe 95% confident that your accuracy will lie within this range. And if it is outside, it's okay, it's accepted, right? So how can we report it? We need to report it in this way. It could be 89% plus minus 1.7%, for example. So in this case, we have upper bound and lower bound. It could be 79%, for example, plus minus 2.2. Can you see this plus minus? And if you want to put it as a percentage, for example, it could be 89%. And this is the range. This is the upper bound and lower bound. So it should be between 87 to 90.8%, for example, as you can see it here. So this is the correct way for reporting your results. If you report your results as a single number, it will not be correct. You will get a question immediately from maybe the reviewers of your article, for example, from the journal, or also in the examination committee. Yes, Christian?
Yeah, thank you.
Thanks.
I agree totally about all of this, but I'm just thinking about the fact that this is classification, right?
Yes.
And this is when you use accuracy as a metric. But what if, for instance, you are doing regression and your results is a metric like R squared or some other metric? Do you think in that case you should also use a confidence interval?
Yeah, why not? Because if you will, if you repeat your results, for example, if you will test your model maybe 10 times, for example, in the times, each time also you will get maybe a regression error, for example. You will calculate the mean value plus minus standard deviation. So it will be a range, right? Because when it's a regression problem, we will get maybe regression accuracy or regression error, for example. So it's the same also. We can just take average and calculate standard deviation and report our results as mean value plus minus standard deviation, for example, right? Because each time you try to regress, I try to regress your salary next year, for example. Maybe I'm correct, maybe I'm not correct. So I can just estimate that maybe next year it will be 1.5 million. Maybe another one he will, maybe if I repeat my results, it could be 1.4, 1.45. So there will be also some regression error, right? So we need to do the same for classifications and for regression problems. Yeah.
And then I was also thinking about in classification problems about ROC curve.
Yes.
Are you going to touch upon that as well?
One more time, please.
ROC.
ROC. Yes, I will do it.
Receiver operator.
Yes. But not today. I will, because I'm just getting feedback from you. I will prepare it for next week.
I was just thinking that this could be some other way to present results, which maybe a bit better than accuracy.
Okay.
And then
yes.
And then we could also ask the same question: how could we signal the confidence interval? Because then the result will be a curve. You can choose a parameter to set your precision and accuracy, and then it might not be that. So that would also be a good thing to discuss. How to?
Yes.
Is it enough to have just one ROC curve, or should we actually?
Yeah. Let me check it this weekend and present it next week. So I can prepare also some few slides and we can talk about it next week, for example.
Okay, thanks.
Yeah. So because it's important to get feedback from you and try to develop those stuff. So I will reflect on it next week, for example, and we can make comparisons. So this is the results with your confidence interval, for example. So we will have the mean value plus minus something multiplied by standard deviation. So we can calculate this confidence interval and report our results, as you can see it here as a range. So how can we calculate this confidence interval for a validation or a test set, for example? So we can report your classifier accuracy in the form of P, for example, plus minus dP. For example, this is a range. And if you need to formulate this confidence interval equals the mean value. So it's X bar plus minus Z multiplied by standard deviation divided by square root of N. N is a sample size, right? And S is a standard deviation. And when you divide this one with this one, it will be standard error, correct? So in fact, it's X bar plus minus this confidence level value multiplied by standard error. And the standard error, of course, it's less than the standard deviation. So should expect that when we do this, it will be more compressed. So this confidence interval, it will be more narrow. So we can say that it's X mean plus minus this Z multiplied by standard error. I mean, it's just a brainstorming. So I try to get a simple approach for doing it. But of course, you can go more deeply and try to explore more in this direction. So mean plus minus standard deviation, for example, standard deviation, it's measure of variability about the mean, correct? So when this standard deviation is high, we can say that there are lots of variability in our model, correct? Because maybe I can get the average as 80% plus minus 10%, which means it's from 70 to 80%, which means my model has too much variability, right? Mean plus minus standard deviation is the most common descriptive statistics used to describe variability in classification accuracy. For example, if your data follows a normal distribution. When we use this approach, we should assume that our data follows normal distribution. And to calculate the mean and the standard deviation, we need to train our model, right? You need to train your model and calculate the error, for example. It could be classification error or prediction error. It could be accuracy, it could be precision. And then we need to repeat this process n times because I need to calculate the mean. So for example, I need to repeat this process n times, but the problem here, maybe the model is complex, maybe training and testing, it takes too much time. So in this case, it will be a problem. But if you can repeat this process n times, you will get, and of course, when you increase n, you will get estimates closer to the true values, right? Because I can toss a coin 2 times, for example, and I can toss a coin 20 times. So when you toss it more times, maybe you will get closer to the true values. Because when we do this, we try to estimate the accuracy, the mean accuracy. So when you increase n, you should get closer to the actual accuracy, for example, because the estimates will be closer to the actual values. The standard deviation will measure how far the accuracy of each individual model from the true value, because if we repeat this one n times, in this case, we will try to find how far each individual model from the true mean value, for example. Standard error will be standard deviation divided by square root of n, or it could be square root of SCD squared divided by n, for example, and it will measure how far the estimated mean accuracy from the true mean accuracy. Standard error is smaller than standard deviation because we divide it by square root of n. And when you increase n, because we divide by n, so when you increase n, it will be also much smaller, right? Which means we will minimize the uncertainty in our calculations. So here we need to train your model n times using a different random seed, because if you fix this random seed, you will get exactly the same results each time, right? So because when we use this so far, when we train our model, we use this random seed equal. We use this try to fix this random seed to a value. So when we repeat our model, our training and the testing, we will get exactly the same results. But in this case, I need to get different results each time. So in this case, we don't need to use a random seed. And we will calculate the accuracy each time, and maybe the accuracy for the test set each time. Then we will calculate the mean accuracy and the standard deviation. A larger standard deviation is an indication of larger variations in your accuracy metric, because maybe each model is performing different, right? If you got a model with accuracy 95%, if you repeat this process and the second model, in the second model you will get accuracy of 85%. It will show you that there are lots of variations between different models. It is the same model, but between different tests. We will calculate the mean and the standard deviation, which is not, calculating mean and standard deviation is not practical, especially with large deep learning models that took long time for training. Of course, this approach, it will not be practical, especially today for people who are working in NLP applications, for example, as you have very large models, and the training takes time, and testing also takes time. So it will not be very practical. So in this case, we need to calculate instead of doing this, because this part here, it requires repeating your testing n times. Maybe we can calculate the confidence interval using a single value. So smaller sample or smaller training set size could lead to larger widths of the confidence interval and vice versa. And this is correct because we divide, in fact, by square root of n. As you can see here, if we calculate the mean plus standard deviation divided by square root of n, so the relationship it will be it's inversely proportional to n, for example. So when we increase n, we will decrease the standard error, right? So the sample size could lead to a larger width of the confidence interval and vice versa, right? If n is, so for example, I will say that if n is small, so in this case, SCD divided by square root of n, it will be larger, right? So it will be the large of the width of the confidence interval, it will be larger and vice versa. For smaller sample size, the information contained will be less, and hence the width of the confidence interval will be larger. So you can, if you need to understand one, because when it's a smaller size, in this case, I have, for example, very small test set. So in this case, we have very less information to test our model. So in this case, we should expect that the confidence interval will be larger because we are not very confident. So when you have a larger test set, it means you have maybe all possible cases for testing your system, and you will be really more confident, or we can say that you will have less, you will be less uncertain about the model performance. So larger sample size, it will give you better confidence. When the sample size is larger, the width of the confidence interval, it will be less, which is good, right? Because this is the confidence interval. So if I have this mean value here, and I have this upper bound, lower bound like this one, maybe I have the same also. I have the mean value here, and it looks like this one. So it's large confidence interval and a small confidence interval. Of course, a small confidence, small confidence interval, it will be much better for us, right? Because here we have less uncertainty. We are more confident that the results will be within this range. And this is the quality of your model, or it's an indication of the variations of your results. because maybe I can get, for example, imagine that I'm buying a car, for example, and it's electric car, for example, and when I charge my battery, for example, I don't know if it can, I can use it for maybe 500 kilos, for example, kilometers, for example, or 450, because I have too much uncertainty. So when this range increases, we will not be certain about the performance of my model. So this one, of course, it's much better when it's narrow, when we have narrow confidence interval. So the interval becomes narrow when the sample size increases. Of course, when we increase n, the size of the interval, it will be narrow, right? Which is much better because we have more information. Similarly, also larger standard deviation will lead to a larger confidence interval and vice versa. When this one increases, when standard deviation increases, of course, because it's proportional to the interval. So when this one increases, also the interval will increases, right? So when you have too much variations, the confidence interval width will be higher and vice versa. So the interval becomes wider when confidence interval when confidence increases and vice versa. Yes. So how can we calculate this confidence interval? I found, there are many approaches for doing it, and this is one approach. We need to assume that my data follows normal distribution, right? And in this case, confidence interval was composed as this one. It will be x mean plus minus z multiplied by standard error. And we need to calculate this one. You can calculate this one for 90% confidence interval or for 95% confidence interval. So it's up to you. Of course, when it's 95, it should be, the width will be less. When it's 90%, the width will be larger. Because when we are less confident, it means the range of the confidence interval will be wider and vice versa. X is the mean. Here, X is the test set accuracy. So we need to, when you train your model, you need to test it with the test set. So we need to calculate, for example, the accuracy for the test set, for example. Z, it's the number of standard deviations, and the SE is the standard error. How can we calculate standard error under normal approximations? We can use it. We can use this equation for calculating it. So it will be square root 1 divided by n multiplied by the accuracy, the test accuracy multiplied by 1 minus test accuracy. And the n, of course, is a test set size. This n is a test set size. And of course, as you can see here from this equation, when n increases, standard error decreases, correct? And then when n decreases, standard error increases, correct? So when you have a small sample, a small test set will lead to higher standard error. And then when you have a large test set, it will lead to a smaller standard error, right? Because when you have a large test set, it means you are testing your model with all possible cases, for example. So in this case, we will be more confident about the performance of my model. So at the end, we need to calculate the confidence interval. Just substitute this one here. So it will be the test accuracy plus minus z multiplied by this square root. So this is how we calculate it. So now we need to test. We need to just test it with an example. I will select also this iris data set, and I will try to use a perceptron, for example, which is binary classification as a binary classification problem. So in this case, I will select the first 100 points. I will select the first 100 points, and I will select two features, feature number 1 and feature number 2. And in this case, also the target features, I will select the first 100 points because the first 100 points are related to class 0 and class 1, because we will solve this problem as a binary classification problem. So my model will look like this one. This is my perceptron. And of course, here we have the summation. And then we have here also the activation function, correct? So first, I need to calculate mean accuracy. I need to calculate here mean accuracy plus minus standard deviation, correct? Just as a classical approach. So in this case, I need to test my model for n times. Because this model is very simple, I just selected n equal 100, right? So so I will this is my data set. I will use this train test split each time, because I need to test my model I try to increase the the variability in my model. So each time I will select different test set. So each time I will have different X test and Y test using this one in the for loop, and my model will be a perceptron. And of course, we import this perceptron from sklearn.linear models. So this is maximum number of iterations. This is learning rate, validation fraction equal 10%, for example. So this is my model. And also I will not use here random seed. We will not use random state, because in fact we can use random state in this function. Remember, stratify, we use here stratify because I need to have balanced data set, which means when we use stratify, all classes, because here I have two classes, so all those two classes will be equally represented in white rain and white test. This is the most important. I need to be sure that those two classes are equally represented in my test and the train set. So in this function, I didn't use random state equal 42, for example, because each time I need to get different X test and Y test. And also when I train my model, when we defined the model also, I didn't use here, because I can use here also random state equal 42. And in this case, those weights will be initialized with exactly the same number each time. So I removed it here because I need to start each time from different random values, right? Because I have those weights, omega 1, omega 2, and the bias. So if you wrote here inside this function that random state equal 42, in this case, we will have a random fixed seed, random seed. In this case, each time when we initialize this model, I will initialize omega 1, omega 2, and bias with the same random value. And we will get exactly the same results, the same accuracy each time. So I will remove this from train test split, and I removed it also from my model. Now I will train my model using X train, Y train. So now, as you can see here, we have some randomness, because each time I will get different X train and Y train, because I will repeat this process n times. So each time I will get different X train, Y train, and for training my model. And also we will initialize the model each time with different random values for omega 1, omega 2, and B. And after training my model, I will just calculate Y predict using X test. And I will use Y predict and oh my God, I did something wrong here. This model score, this one is wrong. Sorry, this one is wrong. It's not X test. It's Y. It should be Y test, comma Y predict. I don't know why I'm getting good results, or no. Anyway, just remember, please, here this model dot score. We calculate the accuracy, for example, but this one is not correct. It should be Y test, and it's strange. Yeah, because it should be model dot score, and the input to this function, it should be Y test and Y predict. Just remember this. And each time we will calculate the accuracy, and I will store the accuracy in this vector, so I can have a list of accuracies. And at the end, I will calculate the mean value of this accuracy, right? And I will round it to 2 digits, for example. And also I will calculate standard deviation. If you want to calculate mean value, it's from numpy, it's nb.mean, and also it's nb.standard deviation, and I will print out those numbers. So now I have the accuracy. If you want to calculate the accuracy range, so it's the same also, it will be this mean value plus standard deviation and mean value minus standard deviation. But the order is not correct. I should get this one first and this one here, because the range here, it should starting from lower bound and upper bound. So please just swap it.
Professor, that model.score, if I use X test and Y test, is it a problem?
I don't know. Model score, is that correct? Really, in this function, we use X test, Y?
I think this is correct.
Okay, so we use X test, Y test, and calculate the score?
Yes, we can do that.
Okay, sorry. So this is, okay, so we can calculate it from here? Yeah, right. So it could be also, I don't remember, because I thought that it will calculate the score between Y test and Y predict. So if it's correct, it's fine. I don't remember, right? So now we have the score, and this score, it will be the accuracy, for example, and we will store it in this accuracy vector. And at the end, we will calculate mean and standard deviation, and we will calculate the range. This function or this line, it will calculate the range, right? So we will have this upper bound and lower bound, starting from lower bound, and also we have here this upper bound. So just please swap it. So at the end, after training this model 400 times, we have those weights. So we have omega 1 equal 0.27, and we have no, in fact, those parameters also for the last model. Yeah. Sorry, those. I mean, this one, it's for the model number n, correct? when I'm printing those model parameters, it's for just a model number n. So this weight omega 1, omega 2 under the bias, as you can see here in this graph, and the accuracy, it will be 94% plus minus 0.08. So this is the mean plus minus the standard deviation. So now it's more accurate to report your results as a mean value plus minus standard deviation. And if you want to calculate the range, you will get the range. I need to repeat these results again with another model. For example, I will repeat it using MLP. And I selected here also n equal 20. And when I'm using NLP, I will select here, it's just my choice. I will have two hidden layers. As you can see here, two hidden layers. And in the first hidden layer, I have eight neurons. And in the second hidden layer, I have 5. So if you want to draw this model, it will be like this one. So one hidden layer, which has 8, so it will be like this. So starting 1, 2, 8. And the second hidden layer, it has 5. So it will be like this. This is now number 5. And of course, in the output layer, I will use here the whole data set, right? So in this case, I will have in the output layer 3 units, 1 for each class. So it will be like this one. And I have here 4 inputs, right? So we have here x1, x2, x3, x4. Just have those connections. It will be like this one, correct? Have all those connections. And finally, we will have those connections. So it will be like this one. So it's more complex model now, right? So it will be like this one. So in the input layer, we will have 4 inputs. Those 4 inputs are the input features, right? So those are the input features from my data set. So in fact, when you define MLB classifier, MLB classifier from sklearn also, you just need to define number of hidden units, hidden layers. When we have here 2 numbers, when you have here 2, it means I have here 2 hidden layers. In the first hidden layer, I have 8 neurons. And in the second hidden layer, I have 5. Maximum number of iterations, 1000, for example. So I used here the activation function, logistic, right? And I used this solver. And the validation fraction also, it's 0.01. And as you can see here, I didn't use random seed. I didn't use random state equal, correct? Just remember here in this MLB classifier, I didn't use random state equal 42 or any way. So we didn't use, so in which means each time we will initialize those weights with different random values. It's the same also because I put here this train test split inside the for loop. It's the same way also I use the stratify equal y because I want the 3 classes to be equally represented in my train and the test sets, correct? I use the test size equal 0.3, which means 30% of the data will be used for testing, and 70% of the data will be used for training. As you can see here, I use the 2 categorical, this function, because in fact, y-train, it's y-train, it's like this one. It's 0, 0, 0, 1, 1, 1, 1, 2, 2, 2, 2, 2, because I have 3 classes. So I need to convert this one into one-hot encoding. So to convert this one into one-hot encoding, you need to use a function called the 2 categorical. So we have the data set in place now. We defined a model. We will train the model using X-train, Y-train. And after that, we will calculate the accuracy using model.score. So the input to this function will be X-test and Y-test. And we will calculate the score. And we will keep those values into this vector. And at the end, we will calculate the mean. And we will calculate standard deviation. At the same also, the range, please, because this is not correct. We should start with the lower bound. Just swap this one. Just swap this one, please, because this is not correct. I cannot have this range from larger to smaller. I should have the range from 0.33 to 0.71. So as you can see here, the accuracy of the model is very low. It's 52% plus minus 19%, for example, or 52% plus 19%, right? If you want to put it as a percentage. So the accuracy here, it will be 52% plus minus 19%, correct? Which means it will be from the range of 32%, you should expect accuracy from 32% to 71%. So this is the range of accuracy. So which means I build this model and I will communicate those the results of this model to my customers, for example. So I should tell him that you should expect accuracy between 30% to 71%, right? because this is a mean plus minus standard deviation. So in this case, we try to report our results as a range. If you try to change this logistic function into ReLU, just try to replace, select a different activation function, because I used here logistic. If you will use ReLU, you will get much better results. It will be 88% plus minus 15%, which means also it will be a number between 74% and 100%, right? 103%. But of course, you need to just cut that part. You can just see it's from 100% to 47%. We should expect, we cannot have an accuracy higher than 100%, right? So it should be between 74% to 100%. So if you will sell this model or algorithm, for example, to a customer, you just inform him that you should expect accuracy between 74% and 100%. In this case, your product will be okay, because if people will get different, but if you told them, no, my accuracy is 88%, and he will use your model and he will get accuracy, for example, 85%, he will not trust you, right? If he will get 80%, it will be strange. If he will get 90%, it means my model has variability. Of course, any model has a variability, so we need to report your this variability in the form of this range. If we need to calculate this, do you have any question for that part? I mean, it's very simple. I mean, it's just I want to do it because usually people, when they try to report their results, they just report their results as a single number, and this single number will not be correct. So try to report your results as in the form of a range. So we have a problem here because I need to repeat my results here for n times. I need to train my model here for n times, and last time also for n times. So maybe your model is very complex and it's too large, and it will take maybe weeks for training. So in this case, I cannot use this approach, because some people really, they use maybe some weeks for training their models. And if you need to do this process for 5 times or 10 times, it will be really time consuming, right? So in this case, we try to calculate this confidence interval using a single number. This is very, very practical. We need to run it once. In this case, we will use random state, right? We will use this random seed because I will run my model only one time, so other people can try to reproduce your results or your range. So in this case, we will use, we need to select this confidence interval. Maybe someone he will select 95% confidence, someone he will select 98%, someone will select 90%, for example. From this confidence, this is the desired confidence level. You need to define it. From this confidence level, you will calculate this Z value, right? We have a function in MATLAB, in Python for doing this. It's scipy.states.norm.ppf. So you will get this using this confidence, desired confidence level, you will calculate this Z value, for example. So for 95%, the Z value will be 1.95, as you can see it here, right? So we will get this number. And after that, I will train my model, calculate the accuracy. Of course, you will use train test split, for example, and remember to use random state also, because if someone else wants to reproduce your results, he should be able to reproduce those results. So we will train our model. We will calculate the accuracy for the test set using X test and Y test. And after that, I will calculate the confidence interval length. So it will be this Z value multiplied by, I mean, this is the last, I mean, we need to calculate that part, as you can see here. This this part, standard error. We need to calculate standard error and multiply it by Z. We need to calculate that part. So we will do this. We will calculate this standard error. This part is the standard error, right? Again, sorry. So we need to calculate that part. That part is, this is the standard error, as you can see. So it's a square root accuracy multiplied by 1 minus accuracy divided by n. This part is the size of the test set, which is n, right? So this part is a standard error. Multiply it by the Z value. In this case, you will get the confidence interval length. You calculate also the accuracy of your model, for example. And now we need to get this, the upper bound and lower bound. So the lower bound will be this accuracy test minus this length. and as upper bound, it will be the accuracy test plus, so it's plus minus, right? Now I need to report my results. So my results, it will be like this one. It will be the mean value, right? Or the accuracy, sorry, it's not mean value, it's just the accuracy, the test, the accuracy for the test set, plus minus this length. And if you want to write it in a range, it will be the same, it will be the lower bound, plus minus, or lower, I mean, it will be this lower bound to the upper bound, correct? And also when the upper bound is higher than 100%, you need to just cut off all numbers greater than 1. So we need to cut off the upper confidence interval above 1, because we don't have accuracy higher than 100%, right? So in this case, we will have this range. So in fact, using this confidence interval, you will be able to report. You will be able to report your results, although you just you ran your model only for one time. So that part is very simple. So please remember to add that part in your test when you train your model and when you calculate this confidence interval. I mean, you can do this for all numbers. In fact, in the confidence in the confusion matrix. So you can just use this confidence interval, calculating all those numbers, and you just need to select your desired confidence level, and the code will do all the rest for you, right? You just need to select this number for 95%. So in this case, we can claim that when we run our model 95% out of 100, or when we run our model 100 times, we will be sure that 95 times out of 100, we will get an accuracy within this range, right? So one time we will get 974, one time we will get 96, one time we will get 99, one time we will get 100%, one time we will get 93%, 94%. So all those numbers will be very correct because we provided a range of accuracies. So if someone run your model in a company or somewhere, they don't have any rights to complain because you didn't provide a single number, but you provided a range of numbers. You can do this one for accuracy, you can do it for error, you can do this for precision, recall. And the calculation is very, very simple. You can just make a function, for example, or you can put it in your pipeline. When we are using pipeline in machine learning, you can just add that part in your pipeline, so it will generate all those numbers for you. And when you are writing your article, instead of reporting those single numbers, you need to report to those range of numbers. It will look very professional. Yes. Any questions, please? We are finishing this first part today. So please let me know if you have any questions. We can take a short break, maybe 10 minutes or something if you want. And after that, we can start again. But before having this break, do you have any questions? Do you have any questions, please? Can you hear me?
Yes. Right. I think
Yes.
this was good.
Okay, thank you very much. Yeah. So if you don't have any questions, we can take maybe 10 minutes break, for example, and we can start again after 10 minutes.
It's fine.
Yeah, okay. Thank you very much. So see you soon.
You.
Thanks.